Thank you for the kind introduction and for inviting me, and thanks everyone for attending this at this late hour. I will first talk about mobile authentication, and later on I will focus on voice biometrics for mobile authentication. Okay, so the need for strong mobile authentication is quite straightforward. Most of us are using mobile devices for accessing applications such as Facebook, so all our entire digital life, private data, maybe even our financial transactions or bank account is all tied through smartphones and tablets. So there's a need for strong security and strong authentication for these mobile devices. Now, plain passwords are not good enough because they may be guessed, peeped at, hacked, and are usually uncomfortable both for remembering them and for entering them. So it seems that biometrics is maybe a good solution for that. And lately we actually heard about, we saw offerings of Apple and Samsung that are actually offering this technology for mobile devices. However, using a single biometric may be a problem because it's usually inaccurate. And it also usually can fail or be impractical in certain scenarios. For example, fingerprint ID is useless for a person wearing gloves or sweating. And it even doesn't work for some people. And that's true for all biometrics, not only for fingerprint. Okay, so to address this problem, we at IBM Research have developed a technology and a system during the past 2 or 3 years for multi-modal biometrics for mobile authentication. And this system is supposed to address most of these problems. So the heart of this problem is, of course, the biometric engines. Currently, we have 3 biometric engines. We have a speaker ID engine, we have face ID, and signature ID. And I will not talk in this presentation at all about the face ID and signature ID components. I will focus on the speaker ID engine. I will talk a bit about the other components in this system. Okay, so first about score calibration and fusion. Well, once you get a score from a biometric engine, you need to somehow to calibrate it, to make it into some meaningful probabilistic score. So the scores from the biometric engines are mapped into likelihood ratios. And this mapping is quite complex because you want to take into account the quality assessments that we can assess from the signals. So basically, we can measure the SNR for audio, we can measure the image sharpness, illumination level, and symmetry, and possibly other features that serve as side information for this score calibration. Now, once we manage to adequately calibrate the scores, the score fusion becomes a much simpler task, and for biometrics, an independence assumption is usually quite reasonable. Policy management is the process of choosing the next step in the decision tree. So we can see here in the right-hand side of the slide a decision tree, which basically explains what the process that we have to go through when we are doing authentication. We start by choosing which kind of engine we want to acquire and apply. So basically, if for example, we measure that we are in a noisy condition, then maybe it doesn't make sense to start with voice identification. Maybe it's better to use face ID. So the policy manager decides which modality is the next the right one for the next authentication step, and also it should decide whether we should terminate and give a decision to the application. Maybe we want to accept or reject the person. So the input for this process is the required confidence level, because different applications require different confidence and security levels, and also previous scores from previous authentication attempts and the current quality assessments. And the way that a policy manager does this decision is that it tries to optimize some cost function, which is combined of two types of costs. The first one is a usability cost of acquiring a modality, and the second one is a security cost, either of having a false acceptance or misdetection. And so the policy manager is supposed to predict what is going to be in the future and to try to optimize. Okay, so to evaluate this system that we developed in IBM, we collected data internally. We collected mostly data on iPhones and iPads, and the results are quite comparable. So for the voice-based modality, we use a passphrase, which is "my voice is my password." It's a fixed password. And the recording is far field. So basically, the handheld device is held like this. So there's an issue of noise and reverberation. For Cairo, we use online signature. So the user uses her finger to just write some kind of signature on the touch screen. And we can see that the results for the individual modalities in the table on the left-hand side, we see that for voice and face we get roughly 1.5%, for Cairo we get 7.2%, and we can see that if we fuse all modalities we get 0.1, and we can see the corresponding ROC curves in the right-hand side of the slide. We see in red, it's hard to notice it, but because there are almost no errors, but we see in red the ROC curve for the fusion of the three modalities. So basically, we get 99.9% accuracy. Okay, so now I will focus on voice biometrics. I will first give a very short introduction and describe the state of the art in like 2 or 3 slides. So basically, the state of the art nowadays in speaker recognition is based on I vectors. I vectors were invented for speaker recognition, but they are actually used for many other speech processing tasks. So what are these I vectors? I vectors are basically a mapping of audio sessions of arbitrary length. There can be a split of a second or 1 hour of speech, doesn't matter. And these utterances or recordings are mapped into a fixed dimensional, low dimensional space, usually something like 600 dimensional. And of course, I will not give the details of how it's being done, but it's based on factor analysis, which is applied on GMM supervectors. Now, the take that we have to take from this slide is that we have this black box, which is I vector extraction, that takes an audio recording and maps it into somehow into a vector. And of course, the metric on these vectors is meaningful. Okay, so how do we model in this I vector space, in this high-level feature space? Well, the state of the art for speaker recognition, and until lately also for face recognition, is probabilistic linear discriminant analysis, or PLDA. So PLDA assumes that the I vectors distribute according to the following equation. Phi, which is the I vector, is a sum of 3 components. The first one, mu, is the mean of the distribution over the whole population. S is the speaker-dependent component. So this is actually the speaker information. This is what we really want to observe and to classify according to this, to S. And C is a channel or nuisance component, some noise component. S and C are assumed to distribute normally and independently with covariance matrices B and W. Okay, so this can be illustrated in this slide. In the left-hand side, we see an illustration of the I vector space. We see 4 different speakers with 4 different colors. For each speaker, we see different dots. Each dot or vector, actually an I vector, is a representation of a single session. So if a speaker green, for example, said, my voice is my password several times in different occasions, then each occasion will be mapped to a single vector and a single point in this I vector space. And we can see here the 2 types of covariances. We see the covariance B, which is the the inter-speaker variability or between speaker variability. And we see covariance W, which is the within speaker variability. And here we assume that all the speakers have the same within speaker variability. Okay, so this actually is a state of the art in speaker recognition. Now what is the problem? Actually, this technology works very well if you have adequate training data to train the PLD model. Unfortunately, the amounts of data that you need is in the order of 1,000 or more speakers and many sessions per speaker, per subject. And what happens when the target data that you want to deploy your system is highly mismatched to the data that you do have? So for example, in our case, we do have the same data that all the research community has, which is based on telephone conversations, and we do have thousands of speakers with many sessions, but it highly mismatches the mobile data that we are using, both in terms of channels and noise level, the length, and the textual content. Okay, so my voice is my password is very different from a telephone conversation of 5 minutes long. So this is a serious problem. And actually, this problem was also a major topic in the recent JHU 2013 Speaker Recognition Workshop, where actually I participated. So the setup there was not about mobile authentication. It was more general. It was the following one. The evaluation data was a standard NIST 2010 speaker recognition evaluation data, which is telephone conversational data. And there were two types of data sets for training the PLA system. The first one was the switchboard data, which consists of phone calls recorded a long time ago, more than a decade ago. And the second one was mixer, which consisted of more recent data. And the two data sets were of comparable size, same amount of speakers and same amount of sessions per speaker. Now, it was quite surprising, and this was a starting point for the workshop, that if we train the system on the recent data mixer, we get an equal error rate of 2.4. However, if we train the system on the older data switchboard, we get an equal error rate of 8.2. And this was very surprising because until this workshop, most of the researchers just trained their systems on both of these data sets, just pulled them together and did the training. So no one was really aware of this problem. The mismatch doesn't seem that high between the data sets. Okay, so this was the research problem. Now, the method that we introduced is called interdata set variability compensation, or IDVC. And the main idea here is that we want to find a projection P in the I-vector space such that the distance between the PLD models for source and target data is minimized. So let I explain it in more detail. In this slide, we see in the left-hand side a box, a blue box, where which represent the source data. And this is the data that we have, a lot of data from it, thousands of speakers, and we can train a PLD model. Now, there's the target data, which is presented as a cloud because we don't have the target data, but let's assume it exists somewhere. And if we had access to this target data, we could train a PLD model from that target data, and that would be ideal. We would train a model from the target data, and it will give very good results. Now, the problem is that the PLD model that we have in blue is very different from the PLD model that we want to have in green. And what we want to do is we want to find a linear projection P on the I-vector space, so it's in the feature space, not in the PLD space. We want to find a low dimensional. We want to find a projection P that after projection, both of the PLD models, the green one and the blue one, are much closer to each other. And if you find such a projection, it's still, of course, we want to reserve most of the speaker information. We don't want to just throw everything and make the models be similar. So this is the goal. Now, the question is, how can we do that when we don't have the target data to estimate P? So the trick here is that we work with what we have. We do have some data. For example, we have the source data. Maybe we have other data sets. So what we do is we divide the available data that we do have into subsets. And ideally, these subsets would be homogeneous. So for example, if we have some data and we know that some of it is cellular phones, some of it are landline phone, this is a reasonable type of partition. Also, if we know that some of the data are females and some are males, also we can try to partition according to this feature. So what we do is we take our development data and we divide it into its subsets, and then we estimate P such that the variability between the PLDA models for the different subsets for our development data is minimized. And in practice, what we do, we notice that switchboard actually consists of 6 releases. And actually, for some of these releases, we have no clue what's the difference between them. Probably that they were coded in different times. That's the difference. For some of the releases, we do see that a difference. For example, cellular versus landline. So what we did is defined several partitions. For example, we took each release into a separate subset, and this gave us one partition. We further partitioned it according to male and female, and we got 12 subsets. And this is another partition. And also we try to have a minimal partition. We selected 2 subsets from 2 releases from the 6, one cellular and one landline. And this is a third partition. Okay, so once we have the partition, how do we find the P? Well, we represent each subset by a vector in the hyperparameter space. So for each subset, we train a PLD model. We have the mu, the W, and the B, which represent the PLD model. And this is a point in the model space. And we can see that for different subsets, we have different points, and there's some variability. And our goal is to decrease this variability. And what we do is we find and remove a subspace of the I vector space that would effectively reduce variability in the PLD hyperparameter space. And we do it, in this work, we do it independently for each hyperparameter. So we start with one hyperparameter, for example, mu, and we compute a projection for mu. And then we compute a projection for B and for W, and we just combine these projections. So for mu, it's very simple how to find a projection. Let's recall that mu is the mean of the distribution of the I vectors in a given subset. So we can just, if you just want to minimize the differences between the mu hyperparameters, what we can do is just apply PCA on the set of vectors, mu sub I, and choose the projection to remove a certain amount of eigenvectors that we found. Now for B and W, it's a bit more complicated because these are covariance matrices, and we want to find somehow a method to reduce the variability between them by removing some subspace from the I vector space. So given a set of n covariance matrices, W sub I, we denote the mean covariance matrix by W hat. And we define the V, which is a unit vector, a direction in the I vector space. And the goal is to find the V that optimize or maximize the variance of the variances. Okay, so I won't go into details, but if we have covariance matrices and we pick a direction in the feature space, then we can project everything on that direction. And instead of having covariance matrices, we have variances. And we can just try to find the vector that maximizes the variance of the variances. And this is how it's being done. Basically, it's very similar to PCA. We do PCA, but we do we find eigenvectors, but we don't do this on the W's. We do it on the sum of the WI squares. And the reason it's being done is written in this proof, but of course, we won't go over the proof. Okay, so now the question is, how can we estimate this if we don't have speaker labels? So in practice, many times our development data is actually homogeneous. and we cannot find the partition of the development data. So what we can do is we can try to find other sources of data that will represent some mismatch. Now the problem is that many times these sources of data are not labeled according to speakers. So we have a bit of a problem. And the way we do that, we cope with this problem is is as following. So it's very easy to compute the mean I vector for each subset, and we don't need speaker labels for that. What we do need speaker labels is for computing W and B. But we can replace W and B with T, where T is the total covariance matrix. So basically what we do, we compute for each subset of data, we compute both the mean of the I vector distribution and also the total covariance matrix. And we do everything on these two hyperparameters. And we can note that for typical data sets, that is data sets that consisting of many speakers, the total covariance matrix T is roughly equal to W plus B. So it's quite possible to replace the analysis on W and B by doing the analysis on T. Okay, so results and conclusion of this work. We started with equivalent of 2.4 when we had a mixed data which was pretty matched to the variation data. And with the mismatch data, it's 8.2. And for the 3 different partitions, we got equivalent between 3 and 3.3. Now, if we replace the GI2 partition if we use the same partition but we do not use speaker labels, then we get an equivalent of 3.5. So it's a minimal decrease in accuracy. So to summarize this work, we managed to recover 87% of the degradation due to the data mismatch on this specific setup by using the IDVC approach, and this is actually a 60% decrease in equal error rate. And it seems that the method works well even if we don't have speaker labels on the data. Okay, so now just a couple of more slides about mentioning some other work that we have done lately. Noise robustness is again a major issue when we're working on a mobile environment. We tried 2 different methods. One of them is to use robust low-level features called PNCC, and the other one is to add noise to the development data and the training data. And the idea here is that we want to we want to decrease as much as possible the mismatch between our development data and enrollment data and our test data. What we can see in the results is that if we just use clean data both for training and for evaluation, we get equal error rates between 1 and 1.5. If we use the system but test it on noisy verification data, we get a huge increase in equal error rates, roughly 8 and 4. But if we use these 2 approaches, we go back to reasonable results, although still there's work to be done, and we're still working on it because there's still some drop in accuracy. And another interesting work is on spoofing and countermeasures. Because, okay, let's say we solved all the problems and we get an equal error rate of 0. Still, someone can try to attack the system by, for example, doing a playback attack. Just recording me speaking, saying my voice and password, and then playing it to the system. Or you can use more sophisticated approaches such as audio splicing or voice transformation and TTS attacks. So what we've done, we analyzed all these attacks, and we also worked on countermeasures for these attacks. And basically, we have results, but this is an ongoing work. This is a real, very important research field. Okay, so my last slide is I want to review some challenges that we are working on. The first one is noise robustness. I talked about it. Spoofing also. Go detection is very important if we're talking about a real product. And GOATs in biometric means a user with a very high misdetection rate. So it's well known that for each biometric, there is a certain percentage of the population that the biometric will not work very well on it. So it's important to detect it as soon as possible and to mitigate it, and we have a work on that. We have a paper on that. Also, adaptation, long-term adaptation, it's very important, and it's also hard to work on it because it's hard to collect data, adequate data, and this is also something very important. Flexibility in defining new passphrases, cross-text, cross-language. And finally, how can we go deep? In speech recognition, deep neural networks have become the state of the art for several years already. And so far, in speaker recognition, no one has managed to do that. That's a very interesting research problem. Okay, and this is an acknowledgement for collaborators on this work. Thank you.
Thank you. Thank you.